I'm going to go ahead and introduce our two speakers today. So our first speaker, we have Chou-Yu Yong. He is a bridge technical manager at Michael Baker International. He is at the Kentucky office, which he continues to provide technical support to the bridge group and mentor the junior engineers. He has more than 10 years of professional experience in the areas of design, finite element analysis, load rating, seismic conceptual design development, as well as QA, QC, and peer review for both conventional and complex bridges. CY holds a bachelor's in engineering since 2007 in civil engineering from the University of Technology, Malaysia, and a master's from the University of Kentucky. He is currently served as the treasurer for the ASCE Louisville branch and has been involved in the ASCE-SEI cable-supported bridges committee. Our second speaker is Francisco Javier Bonachera, I hope I said that right, Martin. He is a civil engineer and bridge design at Michael Baker International. He also obtained his bachelor's and has his master's and a PhD in civil engineering from Purdue University. From 2016 to 2019, he worked as a research engineer at the Bowen Laboratory for Large-Scale Civil Engineering Research at Purdue University, and joined the Indianapolis office at Michael Baker International in 2019. He has ample experience in complex finite element modeling of steel structures, particularly for load rating, fatigue, and redundancy evaluations, and retrofit development. Frank has co-authored AASHTO guide specifications for the evaluation of system level and internal redundancy of steel bridges, as well as made contributions to the LRFD bridge design specifications and the manual for bridge evaluation. Many achievements. So I'm going to go ahead and share give this screen over to CY, and we can get this started. Okay, CY, feel free to share your screen. Yep, perfect. I think you might be muted though. Okay, I hear you. I think.
Good afternoon, everybody. Can you guys hear me?
Yes, we hear you.
Okay, all right. My name is Chou-Yu Yong. I'm the Bridge Technical Manager with Michael Baker, and Francisco and I are going to present about the modeling and analysis side of the emergency repair of I-40 Hernando De Soto Bridge. So let's go to the agenda. So it's unfortunately that we could not tell the full complete story of the emergency repair, but still want to tell to focus more on the modeling and analysis side, of the work we did on this bridge. Then I'm going to talk about the modeling progress, of the work. Then I'm going to talk about the analysis side that we did throughout the 3 phases of the work. And then I'm going to turn over to Francisco. He's going to talk about the best part of the presentation, which is the advanced local model detailing or modeling. Then he's going to wrap up the presentation with the lesson learned. Okay. So just the short version of the story. So Hernando De Soto Bridge is the 2 continuous span tire arch that carries I-40 over Mississippi River. So on May 11, the hangars and the arch inspection team discover a fracture on the north side of the tie on the Tennessee span. So that fracture is about 70 feet west from the middle of the pier. So if you look at the pictures, right, the outside web and the top cover plate of the tie is completely fractured. Then there's partially of the bottom flange was fractured. Then also on the inside inboard, the top cover plate is unzipped from the inside web. Then the cross section of the tie is kind of warped and misaligned. So the inspectors recognize the critical of the finding. So they alert the team of the situation, notify the client, and most importantly, quickly close the bridge. So although Arkansas DOT is kind of responsible for the inspection side of the contract, and Tennessee DOT is responsible for the maintenance and repair of the bridge. So they retain Michael Baker as the engineer of record to do the emergency repair because of our previous experience, and our inspection team is readily available on the site. So all parties kind of acted swiftly, and the information was coming from different angles. So, but we managed to establish a three-phase approach to repair this bridge. First is to evaluate the fracture situation, and most importantly, to stabilize the structures. Then the phase two is to have a permanent repair of the fracture. And lastly is to inspect and assess if other location of the tie has the same fractures or not. So Michael Baker is able to put together an emergency response plan. So, actions taken in the first 24 hours, right, were essential to get us headed to the right directions. So we start to gather all the data that we can access to: bridge plans, shop drawings, design drawings, and inspection reports. Models have been done, test data, and some old construction pictures. Then we mobilize the team. This is required a big, large team to work on it. So we have an analysis team, we have the phase one repair team, as well as the phase two repair team. And other activities going on is like we have the management and keep continuous communications and meetings with the owners. And we also have the BIM modeling team that develops graphics for the PR purposes. So just want to give you a sense of the urgency, how urgent and it is. So within a week of timeline, there are so many activities and decisions being executed, including closing and opening the navigational river traffic, and we have the drop plans, we have the CNGC contract advertisement, and selected the Kiewit as a CNGC for this bridge repair. As I mentioned, that we recognize how aggressive the schedule is, as well as the importance of the work we were doing. So I want to say that this is really a team effort, and analysis is part of the, I guess, important piece of the work. So within the analysis team, we kind of subdivided and into two different teams. One, we have the MIDAS, team that, and within the MIDAS team, we also have a modeler for the global model, as well as to develop the local model, and also investigate, doing other parametric studies. Then we also have the independent model, just to have a good comparisons, to the MIDAS model to increase our level of confidence of the work we did. So on the model development, we start simple. We start with the 2D model because we have an easy access to the existing plan to extract the geometry and input into the MIDAS and created the simple 2D model. And starting 2D is good because it's easy for us to troubleshoot and debug the model if anything, just to get us to the right directions. If we have a more advanced model, it's really hard to find to troubleshoot. So, and then we use the 2D model to check against the existing drawing and the forces and stresses, just to make sure that we are actually capturing the correct behavior of the bridge. After that, we expanded the 2D model into a 3D model. And we also comparing the design drawing with the shop drawing and want to incorporate any discrepancy between those two sets of drawings into the model. Then we did the steel dead load calibration to sort of reasonably accurate or matching up with the total steel weight shown on the drawings. So based on the information that we found on the old construction pictures, the bridge was originally constructed with a temporary shoring. So we felt that we are capturing this correct with just turning the gravity on and not going through to do more complex, staging of the model. So the bridge went through a major rehab in 2003. So the bearings of the arch were replaced with friction pendulum bearing, and some of the members on the ribs as well as the floor system were strengthened. So we did at this phase, we would have to stage the model to capture those retrofit. And then we recalibrate the dead load of the model to match with the total steel weight shown on the drawings. Then we also have a local model. So we started the local model with MIDAS Civil, but we somehow, and this is a very unique and scenario of cases that we kind of hit the limitations in MIDAS Civil. So we will have to use FEA NX to do the local modeling, which Francisco is going to talk about. Other than the analysis side, we managed to use the MIDAS Civil to export the model into a DXF file for the BRIM team to import into their program to do the rendering that was used for the PR or media purposes. So I mentioned that we have another team that developed an independent FEA model just to have, so the goal is to have the two models running parallel of each other and cross-check each other to give us the more confidence of the analysis that we perform. So we had few checkpoints, along the progress to compare the results between the two and reconcile any differences, in the assumptions and results. So as we know that every program, every model has its own nuances, but we still get a very comparable results between the two models. So now I'm going to get into the phase 1 repair. So in phase 1, we did the assessment, to figure out where did the load actually goes when the tire fracture. So we did some sensitivity analysis, that we felt that if when the tire fractures, some of the load may go into the floor systems. So we did that sensitivity analysis to evaluate where the load actually goes. Then we also did some field observations, especially on the friction pendulum belly, if the bearing move or not after the tire fracture. That's when we kind of developed the local model. So in MIDAS Civil, that the local model is not the whole 3D global model of the bridge. It's just solely on the upstream T22 to panel point T22 to T1023 tile location. As you can see that on the pictures, right, we integrated this shell element model into the 3D global model that we originally connected, both ends of the shell model to the beam element of the tile. So we are using this model to assess the yielding and strength just adjacent to the fracture location. As you can see right here, the final mesh, is where the fracture is somewhere right here. So we have a final mesh in this region. Then we make the mesh a more coarse mesh, outside of the fracture region, so that we can get the model to run faster. So based on what we observed from the initial stability assessment, that we can see the significant deflections, visible and in the field in the model that kind of match up or corresponds to what we have seen on the field. So the deflections due to dead load, right, is not a random, so where the fracture kind of surface kind of bound out. So that kind of indicated that we captured the reasonably accurate boundary conditions, in the detailed model, because of, and also our material nonlinear analysis of this local model is reasonably accurate as well. So in phase one, the repair is to install a temporary plate, over the fracture member, just to stabilize the bridge before the permanent repair, design and construction of the permanent repair. So in phase one, so we know that the bridge was closed for traffic. We need to know the bridge was closed to traffic, and that we need to know that what is the safe load, that we could put on the bridge, because for the construction activities, and we ran the influence line analysis, as you can see on the screen right here, that could the star represent the fracture location. So then putting the loads on the Arkansas side would not induce more tension into the tile. So that's why what I'm going to talk about later is that the plate delivery is going to come from the Arkansas side, not the Tennessee side. So in order to facilitate the installations of the temporary plates, the contractor we're going to install the working platform underneath the deck on the floor systems. So we also adding in the platform loading, make sure that the additional load that induced into the tie would not exceed the safe load that we determined. So other than that, we did some construction support analysis, with the contractors means and method to install the plates and how the contractor would like to do the hoisting. So those were all additional dead load analysis that we added into the model, and to determine that those loads would not exceed the safe load that we have determined. Next is the phase 2 repairs. This is when we going to do the long-term retrofit of the fracture sections. So there were a lot of ideas and repairs options being considered for the phase permanent repairs, including replacing the whole fracture tie. I mean, unfortunately, we don't have enough time to go through the options one by one, but the final, I guess, repair options, right? After working with the owners and contractor, the final option is to plate both sides, over the tie girder with the existing tie to remain. So the plating starts from like panel point T20 to L24, where the fracture is actually located at T22. So then post-tensioning was also used to detension the tie and transfer the load from the existing plate to the new plates. So I want to talk a little bit about the design criteria of the plating. So the objective, right, of is to post tension the tie to a reasonably level, so that the plating can be installed to the existing tie, and also to restore the tie the fracture tie that warp to its original geometry. So give you some sense of the level of the magnitude of forces that on the tie. So the tie dead load is about 4,300 kips, and we target that we can PT about 3,000 kips out from the tie. So then the net stresses in the tie is only 30 KSI. And also the post tensioning is kind of limit on the drag force, which I would explain later. The drag forces is the forces of the tie on the tie outside of that post tensioning operations. So the reason we want to do the post tensioning again is to restore the geometry and give everybody a more comfortable environment to do the plating. The new plates has plenty of reserve capacity, under the LRD design. So to help the plating design team, we ran the analysis, the dead load and live load analysis, and provided those demand to the design team, to the plate design team to design the repair. So in addition to that, we also did more construction support analysis, like we mentioned before, is that there were more platform that were installed on the bridge to facilitate the erection of the plates. We also kind of did some sensitivity study because the ladder bracing is kind of in conflict to the new plate installation, that we have to run the analysis and come up with a temporary bracing systems for the contractor to brace the bracing. So other than providing the loads to the plating design team, we kind of implement the post-tensioning, operations into the model and run the PT analysis. So we sort of model the PT rod as the truss element and apply effective PT forces to it. That's where we can look at the drag forces and how efficient the PT is on the bridge. So using this model, we also develop what we call a PT cookbook. Basically, is to bound the solutions between the rigid and flexible model, and develop a plan and a chart for the PT field crew to use. In addition to that, we also developed a local model, using MIDAS Civil for the PT welder and weldment. So the model is to evaluate, the stresses of the weldment, just make sure that the PT operation, does not overstress the weldment. So just to give you a comparison of how it looks like in the MIDAS model, as well as what actually is on the field. So before the PT operation and monitoring, so the strain gauges and the dynaforce sensor were installed on the field location of the bridge. So the PT operation was actually scheduled on the weekend, if I remember correctly. Then during the PT operation, the analysis team is kind of on the standby mode, So we have every model that we use ready, and in case that additional analysis is required, so that we can quickly make the evaluation if something unexpected had occurred. So the analysis team is kind of acted like a control room, monitoring the strain gauges, reading on the type. So you can see this is the example pictures of the dynaforce reading of the PT rod. So looks like we are prepared for everything, but we are not. So we sort of under predict the stiffness of the structures. And if you can see on the graph, the blue dot is the actual drag force reading compared versus the compression force in the type. The forces in the type that we are able to take out using PT. The red graph is the original stiff model, and the gray graph is the flexible model. So we are kind of under predict the stiffness, because in the strain limit stats, we kind of model for the boundary condition, we model the ribs as pin, the floor system, the floor beam the stringer connection, the floor beam connections as pin condition. But in reality, in the service condition, right? They have some rotational rigidity in it. So because of that, we quickly adjusted our model to capture the rotational rigidity of the connections, and we pull out the result and replot the graph that comparing to what actual reading on the field, it is reasonably close. So, but we have to stop at the 600 kips drag force limit. The reason to that is that we look at the real, actual load that we think that will be on the bridge is 675 kips. And in addition to that, the objective was to restore the warp section of the tie. So, and part of the load was transferred already from the existing section of the tie to the new place. And we met the objective. So that's why everybody's agree with the decision to stop, the PT at 600 kip drag forces. So for the phase 3 repairs, the analysis teams play a minor role to it. We just basically providing the dead load and the live load, as well as a seismic load for the plate design team to evaluate, to design those plates that needs to on the other locations of the tie that they might have the fracture. Yeah. And now I'm going to turn it over to Francisco to talk about the advanced level local assessment.
Okay, can you guys hear me well?
Yep, we hear you.
Okay, well, you can go to the next slide, see why. Okay, so the reason why a local model was developed, it was because there was a number of local concerns around the area where the fracture occurred in the tie. The first concern is that there was extensive yielding on the remaining section. A preliminary sort of design calculation of the estimated that after losing the top and bottom cover plate and the outside web, a typical design calculation would have concluded that the rest of the tie would have failed under its own self-weight. So obviously the tie didn't completely fail, and we were wondering how much capacity was actually left in that intact between commas plate. The second concern is that we wanted to evaluate what was the effect of residual stresses. When there is like a large amount of plastic deformation in a plate, there are localized residual strains might form, and you can have some form of buckling during the unloading. We wanted to make sure that we didn't have any strange situation where we have any sort of local instability. And then finally, we also wanted to look at the local effects of the retrofit operations, whether if we were going to remove a particular gasket plate, or if we would decided that it was necessary to detach some of the bracing from the tie and the floor beam, what was gonna be the effect on that that area where localized plasticity has happened. And we also wanted to look at what would be the effect of unbalanced PT forces during the operation. So if you want to go to the next slide, see why. Okay. So why wasn't the local model fully done in MIDAS Civil? Why was FEA NX used? The first thing is that the reason is that we needed an incremental analysis. That is, we needed to include all the construction steps. We needed to start from the scenario where we have the dead load in the tie, and then add the different retrofits, add the different post-tensioning, and see what was the response of the system to it in a sequential manner. Within that, we also, in order to estimate whether any sort of local instability is going to occur, you need to incorporate large deformation theory, which in this case, or nonlinear geometry. And you also need to include a nonlinear material model. You need to include the effects of plasticity in order for those residual stresses to form. Within MIDAS FEA NX, you cannot really successfully do these three things together. So that's why we went to this other tool offered by MIDAS, that is FEA NX, that allowed us to do this incremental, fully nonlinear analysis. So next one. So just a little bit of a summary of the geometry. As CY previously explained, the geometry was originally developed in MIDAS Civil and then was imported into FEA NX. After that, we extended a little bit more of the geometry of the local model to include the tie segment that is between the joints L24 and T20. L24 is the one that is at the middle support of the structure, and T20 is 4 panel points away. So that will leave the fracture that was at T22 approximately right in the middle of the model. We included also the diagonal bracing that was at T22, including the connection plates and any of the plating that was installed during the fracture retrofit, as you can see in the lower image. To model boundary conditions were applied at the L24. The local model was assumed to be fixed at L24, and that would be basically, as I said before, over the support at the support over the pier, and the rest were translational constraints were applied to model the effect of the floor beams and other bracing elements, the framing to the tie away from the fracture surface, away from the fracture location. Yeah, you can go to the next one. Regarding the mesh, all of the elements utilized are shell elements used to model the plates. There were elastic links to model the bolted connections. And for these elastic links, a linear elastic relationship was used basically to be representative of the bolt shear stiffness. The mesh size away from the fracture location, that is the coarser mesh, was 8 elements across the tie height and width, and with a mesh aspect ratio less than 5. So basically, no edge of any element is larger than 5 times the narrower edge. And then around the fracture location, the mesh density was increased to about 1 inch by 1 inch elements, and at the corners of the cracks, we did a little bit of a procedure that is typically used when doing more fracture-oriented analysis. This is an approximation, but we collapse the mesh around the crack tips. This helps with integration, and actually, if you were to do a little bit of a mesh sensitivity analysis where you have the mesh or double the mesh, this sort of procedure helps you with convergence around those areas. At the crack tip, you won't get convergence, but like within an element, you typically get pretty good results. You can go to the next one. Regarding the material models, we use Isotropic von Mises material, so your typical metal plasticity, J2 plasticity. It's linear elastic relationship followed by isotropic hardening. For the steel tie used in the tie, that is the A514 100, also the 10, we use isotropic hardening. The curve was developed based on a Rambert-Osgood relationship. For the rest of the steels, A36, A709, 50, and A709 HPS 70W that were used in the retrofits, and then the A36 into the internal stiffening plates. For those, we just use linear elastic with perfect plasticity because there wasn't many spots that we were getting even that close to yielding. And then the area where the PT forces are applied in the model was modeled as linear elastic. Not a lot of detail was really devoted in this local model to this. This was just to make sure that the forces were transferred adequately throughout the model without much distortion to the tie itself. You can go to the next slide. Okay. So regarding the local behavior, the post-fracture local behavior. The first thing is that after applying axial demands to self-weight, we were able to corroborate that there was like significant yielding developed, particularly on the outer surface of the inboard wet plate. Pretty much throughout the outer surface, at the surface, the yielding would have been reached over much of the height of the plate. However, when we look at through the thickness sort of average value, we see that the average stress through the web was actually below yield. If we look at if we look at the bottom flange, you can go to the next slide. The bottom flange picked up a very large amount of plastic deformation. It was almost as if the whole remaining ligament on the bottom cover plane had been cold worked, had been basically plastic deformation was reached throughout that entire remaining ligament. If we go to the next one. So the first part was to see whether we had any additional capacity in that web plate, and it seems that although we were close to yielding, we still have some additional capacity in the remaining web plate. We weren't really that close to a full section rupture of the yield or rupturing of the plate. And the second concern, going back to the concern, was like the formation of residual stresses. So we were wondering if like a large amount of residual stresses were going to form in the inboard web plate that would create a buckling problem during the unloading or maybe a localized instability. What the analysis revealed after removing those axial forces that we put it in the initial step, although in practice it's impossible to remove all the axial forces. In this case, we basically wanted to go all the way to see if there was any issues. What we saw is that very small residual stresses really form on the web plate, and where they formed, they were localized to the areas near the crack tips, or that particular area that is near the connection to the gusset plate. So the gusset plates are removed, and there was like those are basically the extent of the residual stresses in the web plate. However, obviously, in the bottom cover plate that was almost cold work, you did have like very significant residual stresses, compressive stresses forming. When you were to unload the tie completely, as it was shown in the next slide, that bottom cover plate will completely buckle, but the overall stability of the tie wouldn't be compromised. Once we have reached that conclusion that we could like safely unload the tire without having any sort of like concerning local instability issues. We use this local model to incorporate the different alternatives considered during the retrofit. As Siwei explained before, there was like a myriad of different options that we looked at, whether to cut this diagonal, remove this diagonal, leave this diagonal, cut the gusset plates, do we leave the floor beams, do we, etc. And the main use in itself of the model of this of assessing the effect of the retrofit operations was to estimate the local effect of the unbalanced PT forces. So if you go to the next slide. So we basically created our full, PT incremental PT schedule and added in there some unbalanced forces. So basically, there were 2 positions for the PT. There was 8 outer anchorage points and 8 inner anchorage points, positions A and B. And then you would have an unbalanced force at each one of the corners that it was about 30% of the maximum load that the maximum PT load applied at each tendon. The reality is that because the PT was applied 2 panel points away, and there were 2 connection points between the point of application of the PT forces and the location of the fracture itself, those eccentricities that would develop quite a significant moment at the point where PT is applied, because of the boundary conditions, that the gusset plates, the bracing points will impose on the tie, will not be very significant at the fracture location. The second, if you can go to the other slide, the second use that we gave to this local model, it was try to resolve the feed-up issue, a little bit of the feed-up issue that is encountered after the whole PT operation is completed. Well, the geometry itself was closer. Well, the geometry of the tie itself was closer to our working objectives. There was still a little bit of distortion at the fracture location, as you can see in the top image. So there was a necessity to basically square that box. The problem that we had in here is that if you attempt to do this by the use of localized application of localized forces in this local model, because you have that region on the bottom flange that was pretty much cold work, in order to square the box, what you're doing in the model is basically you are reworking that region. You are again applying forces to overcome those residual stresses and then re-deform that region. So you end up with pretty high demands for that squaring to be accomplished. However, when the steel workers go out there to basically to square this, they can apply a variety of through conventional methods, they can apply a variety of restraints that are difficult to actually model closely or to be modeled closely in FEA NX, but that are sufficient to close it. So in this case, the way we looked at this in the model wasn't really how the repair procedure went, because with conventional methods that they use for feed up, basically just conventional chain and some hoisting, they were able to close the gap to within a working tolerance, because that's the other part in our model. You're trying to deform square this section to make it perfectly square, whereas in reality you are fine if you're working without a little bit of tolerance, and in this case it makes quite a bit of difference in terms of the forces necessary. So if you can go, so here there is like a little video of the retrofit sequence modeling. You can see the application of dead load, the removal of one of the inboard plates. Then as we are applying a little bit of the PT forces, the unloading that it takes place. So gradually unloading. Then eventually you will see the outer plate starts to buckle out because of the compressive forces. Then it's removed along with the removal of the fracture location. And the final stage, and then the final PT forces are applied, which is basically you can model the entire repair procedure for the local model fairly accurate. And in terms of the local behavior, it matched up pretty well with what was observed in the field. So if you go, so now like the lessons learned, the important slide, I guess. The first one is collaboration and communication are extremely important. This is what we have touched in here. It's only the analytical part of the or the structural analysis part of the problem, and that is still itself requires a lot of communication and collaboration because we were simultaneously working in like 3 or 4 teams at a time. But there is a whole other side that we didn't touch on that much. That is like all the other teams that were used in CAD production, in design of the gusset plate, in design of the, sorry, not the gusset plate, in design of the tie splice plates, and construction collaboration with also the construction folks. So this is a very multi-dimensional problem that requires quite a bit of collaboration and communication. From our side of things, the main thing is to start simple. The reason number one to start simple is because you cannot afford to carry out a mistake throughout this work that forces you to go all the way back to make changes. You have to go very simple and very little by little, which is counterintuitive when we are talking about a bridge closure, particularly a critical bridge that we need to open as soon as possible. We want to have as soon as answers as soon as possible. But the reality is that you have to start simple and add layers of complexity as you need them to this analysis. The third part is you have to understand the limitations. Usually, sometimes sometimes in some problems you will reach the analytical capacities of your software, or the ability that your software has to look at a problem, and you have to start looking into other solutions. With MIDAS, we reached the what we could do with MIDAS Civil, and we were fortunate that MIDAS also have an advanced FEA software suite, FEA NX, that we can communicate with one software and another. The fourth lesson learned is regarding the analysis assumptions. So conventional FEA handbook will tell you that your finite element model will typically behave more stiff or stiffer than the reality it is. The issue is that sometimes those are really when we are looking at ultimate capacity of the tie, or where we're looking at a strength level. A lot of times we're making assumptions that are, because we're also geared that way. We, as engineers, as structural engineers, we're geared first to look at ultimate capacity and what works right at the point of failure. But when you're looking at service or in-service conditions, those assumptions don't necessarily relate well, and sometimes it's complicated. In this case, for example, I'm talking about when the drag forces were actually higher because the stiffness of the system was higher than was initially anticipated. The convention is to model connections that are not designed for flexure as to be able to rotate. The problem is during in-service, that is not necessarily true. So you're sort of, in most of these cases, you should be forced to bound the problem. Unfortunately, also for most of these in-service conditions, to come up with an actual relationship that is a real solution to what is the stiffness of that particular point, or how to incorporate the whatever incidental transfer of load you had through friction with the deck, because the deck was actually non-composite, but there's a possibility that there was some transfer of load through it too. That's very difficult to estimate. So with these analysis assumptions, when you're looking at in-service or in-service conditions that are not really a strength level analysis, you have to sort of check them and think about them more than once. And finally, there is a little bit of a friendly reminder. Don't assume that the field conditions are the plans. There's a lot of modifications that happen over the years, particularly with older structures. And there might be member retrofits or something that aren't really in the plans, or that were not in the plans. The plans provisions change. There are construction changes that don't get logged. So that's another thing. I don't know if Siwei, do you want to add anything to this?
No, I think you covered it all really well.
You guys hear me?
Mm-hmm.
Okay, we do have a couple of questions. We are running a little bit late. I don't know if you guys have a couple minutes.
Before Lucy, you get to the question, I just want to acknowledge that the owners TDOT and RDOT with for their continuous support and confidence in the work that we did, and also we had a good collaboration with the owners rep HNTB as well as the contractor Kiewit. And last but not the least, everybody in the Michael Baker team that worked, put in a lot of hours and effort to make this a successful repair project.
All right, yeah, absolutely. Thank you.
And just for the information that the bridge was actually fully open on August 2nd, after 3 months, 2 to 3 months closure. Thank you.
Thank you, guys. I actually was gonna ask if the bridge did open up. I wasn't sure. But yeah, we have a few questions. Do you guys have a little bit of time? We can go over some of them.
Sure.
Yeah. Okay. I'm gonna share my screen then. Give me 1 second. Okay, can you see my screen? Can you guys see my screen?
Yes.
Yeah.
Yes.
Yeah.
All right, great. So yeah, starting with number 1, what was the reason for the fracture, i.e. fatigue, brittle fracture, overload, sorry.
Are we able, well, before we answer that question, Siwei, are we able to do it?
If you're not, it's totally okay. We can skip over it.
So yeah, I mean, I can give a high level, answer that it was actually a weld fracture, the poor weld quality that back on the 60s, but that's the detail of it, that it's I'm not that competent to say about it, but it will probably be presented on other presentations.
Yeah, we are also, I think this also is the sort of like, if we are like talking about sort of metallographic study or something like that for the fracture, I think this is still undergoing, or is still, and it's not, we weren't really tasked with it. So I think this one is for someone else to answer to.
Okay, sounds great. So moving on to number 2 then, when the local model was created, would it have been a good alternate option to apply in force displacements as boundary conditions rather than fixed and rotational BCs?
So we did look at this on the at the effect of like the different boundary conditions, and we compare it with the global model. I mean, obviously you can go about it both ways, but it would be a good alternative too. Yeah.
Okay, and then number 3, what was the load rating of the existing bridge before repairs?
We are not really clear what is the load rating of the existing bridge, but I would say that the fracture is not a strength issue, it's more of the quality of the welds of and the material itself.
Okay.
But right now we are right now doing the load rating, for the post repair.
Okay, and then number 3, I'm sorry, number 4, given the structure has decent redundancy, have the forces and the other members, such as cable, steel, arc, etc., were they looked at?
Well, I would like to clarify one thing here. The tie didn't completely fracture, so the tie was still carrying a large amount of. It was still carrying at least the dead load of that it was supposed to carry in after the fracture. It's not like the tie was unloaded. So I don't know if we could really say that the structure itself has decent redundancy because from an experimental point of view, because we didn't actually have a full failure. But during the process, there was the global model was used to see whether there were any other issues in other members too.
Okay, next one is, has any fatigue/fracture analysis been done to identify the source/cause of the fracture?
Do you mean the fracture of the tie?
I'm not really sure. Sri,
So
if you
if it's just a local weldment, right? The local weldment is just a temporary, I guess, piece that installed on the bridge for the PT operation that is removed after the PT and after the new plate, the new permanent repair plates were installed.
I think that this question number 5 is also, it sort of ties with the first one. I think that is a part of the study that is not really, we weren't really tasked with, and I would rather have the guys that are in charge of doing that, which is not Michael Baker International. It's another company is doing that analysis as a third party, and I think they are once I don't want to jump to conclusions before they have actually released anything.
right. So Sri did confirm it was the tie fracture, just to confirm that. Okay, thank you guys. Number 6, were steel coupon tests used to model the actual steel material strengths versus minimum design strengths?
No, we did not have that data during the development of our models.
Yes.
But I don't know. Yeah.
So because of the aggressive schedule, we are using, the limited information that we have and the best available information that we have to run the analysis. Yeah.
Okay. Number 7, how were bolts of new cover plates tightened since there was no access from inside?
Sorry.
So new cover plates.
There was the you can answer it, Siwai.
Well, honestly, that is, I will have to defer this to the plate design team, and the construction part of it, but so maybe I can defer. I mean, I can pass this question to them, and maybe I can get back to you later.
Okay, yeah, that would.
Yeah. I am under the impression that they were able to get someone inside the tie.
Yes.
that it was, there was during the, and maybe we didn't touch on this, during the retrofit operations, the area where the fracture was cut out from the tie.
So
And
you're correct, Francisco. I just get the confirmation that we cut the new hole and cover that afterwards. Yeah.
mm-hmm. So I think they were able to get someone inside. Yeah, it's a tight space. It's pretty tight for even for one person, but I think they were able to get someone in there.
Okay, and then number 8 was the fracture location. Was the fracture location been able to be predicted by the model analysis? Were other possible fracture locations investigated?
So during the phase 3, right? We went through. We did the inspection of the tie to kind of and testing to locate that potential poor, I guess, quality weld or something that could potentially fracture. And then we did the phase 3 plating over those locations.
Mm-hmm. Regarding like prediction of fracture locations, yeah, and this is also like, I think it will tie also with the question number 9 too, is that this is this is a fracture that emanates from a poor weldment. This is a discrete defect. Now we don't know if there was like an actual like fatigue growth and then it like unzipped briefly, or if there are other issues regarding with the steel, but it emanates from a poor fabrication or a bad fabrication spot in there. Now, the only to prevent both those, if you don't know where these locations are, which you don't, because this is a large structure that is like several decades old, and you will need to know where these like poor areas are, and the reality is that you don't. So you have to rely on inspection, and you have to rely on the inspection folks to pick up any possible problems that we will be developing over the years. Thank you.
So for your information, that there were like 30 locations with core. We took the core out of 30 locations, and there were 20 locations were plated during the phase 3.
Mm-hmm. So there were additional, but it's like in order to predict the location of a fracture, you would really need to. It's not a straightforward procedure. You can like look at regions that you think are going to be more critical, and that's about it.
Okay, thank you guys for that thorough explanation. I'm going to go over number 9 since we just went over that, and then number 10, why was PT necessary, and can we just add a plate to the tie to transfer the load?
So there are a couple reasons to it. I mean, the first one is that the tie section, the fracture tie was warped, the section warped. So the PT is needed to restore the geometry so that they can do the plating over it. And secondly, I mean, the contractor expressed their concern of drilling holes over that fracture locations, because it's a non-redundant member. If something happens to that fracture location, the bridge might fall down. So, and that's why we need to, I guess, take away some of the tension forces in the tie, using the PT.
Okay.
And if you remember, originally the plating was, only starting from the T22 to L24, and for that reason, not drilling at the fracture location. We are actually taking the plating over, from T20 to L24. That's kind of another for your information. Yeah.
Okay, thank you. Two more questions and that's it. So, what was the load path through the structure after the fracture?
So as I think, as I explained before, there wasn't a full fracture of the tie, so there wasn't really a full alternative load path developing. The tie was still carrying dead load. So there might have been some incidental transfer through the bracing on the floor system, but in reality there is not. There was not like it's not a full fracture where you had a fully alternative load path developing.
Okay, and the last one, tie lost 3 sides. How is the tie able to most of the load after fracture? I'm not sure what that means.
So
Yeah, Sri, can if you're still here, can you explain a little bit if you have time, really quickly? If not, we can just skip over that one.
well, the tie lost 3 sides, but the only segments of the tie that you are really relying on capacity are the 2 web plates. The cover plates are not actually designed to carry load. They are just as cover plates. So what you lost is, in terms of design capacity, you lost 50% of your design capacity for that tie. If you take into account several like load factors and that you might use, and back on that day, it's like the safety factor. The reality is that you have at least enough capacity to carry dead load, but take into account that it was close to yielding. It was so there was it was right about there, but it did have sufficient capacity that remaining web plate to carry load.
Okay, yeah, Sri just confirmed he wanted to know how is the tie able to carry the load. That's what he meant. But he's, yeah, yep.
Mm-hmm.
Great. He said that seems to suggest there's enough reserve capacity and system redundancy. Okay, we're kind
of a little bit of over in like a little bit. The tie was a slight. Let's say that you could say that it was a slightly over designed. The member. But to me, talking about redundancy, you would have to actually, in system level, you would have to actually look at it from the point of view of it failing completely, because it's still carried load.
Okay, perfect. Yeah, so I think that kind of sums up all of our questions. Thank you guys so much for this session, for your patience on these questions. I know we have a lot. So I appreciate you guys taking the time to answer them all. If anybody else has any other questions, feel free to email me and I can forward them to them. But yeah, thank you guys again so much for this amazing session. I know all of our attendees really enjoyed it. And thank you all for joining us today. And yeah, if either of you or anybody else in the audience have any questions, whether it's about the software or about this presentation or anything like that, feel free to email me or email the team at grow@midasoft.com. But yeah, thank you guys again so much. Have a great day.
You too.
Thank you. Bye.
Bye-bye.